Good day, guys. So today we'll be talking of physics 101, dimension to be precise. Now, before I move to that, I want you to know that we have seven fundamental quantity or so. But for dimension, we only make use of three fundamental quantity. Now, for dimension, the dimension of a physical quantity is just like how a particular quantity is related to the fundamental quantity. That's what dimension does. Like dimension is used to relate a physical quantity to the fundamental, like a physical quantity we are finding the dimension. We use it to what? To relate them to their fundamental quantity. Now, for instance, let's say now the three fundamental quantity I was talking about initially are what? Length, mass, and time. So these are the three fundamental quantities that we use their dimension to find the dimension of a particular quantity. Now for length, the dimension is L. All categories of length, whether distance or radius or displacement or height, all those ones, they are categories of length. They fall under length. For mass, we have capital letter M, and for time, we have capital letter T. Now these are the three fundamental quantities we use to find the dimension of a particular quantity. So now, today what we'll be dealing with today is now, for instance, before we check the validity of an equation, whether it's correct, because that's also another aspect we can use dimension to do. We use dimension to verify whether a particular equation is correct or not. So now, but before we move to that, let's just check um some quantity like velocity now. You know the velocity we can, this guy is what? Distance, displacement over time taken. And I told you initially that we have categories of length, like displacement, like distance, like height. So this displacement still fall under length, which means the dimension for displacement is L. So this guy has a dimension of L, and for the time taken has a dimension for T. Now for velocity, we can deduce that velocity has a dimension of L per T, which is something as L T raised to the power minus 1. Now that's that for that. Now, but this is not our business for today. Our business is first of all checking the validity of an equation or otherwise. For instance, take the equations of motion for instance. Let's say v square equals to u square plus 2s. Using dimension analysis to check whether this equation is right or otherwise. Now, the dimension for velocity is lt minus 1, and here we have square, that's v square. This u is also velocity, which is something as lt minus 1 square plus 2. This is acceleration. Our a is acceleration. And acceleration is lt minus 2. And s is what? L. Are we together? This is s is distance. This is acceleration. This is velocity. This is also velocity. So here we have lt minus 2, like L square, t minus 1 raised to power 2, that gives us t minus 2 equals to L square t minus 2 plus 2 into, now this L multiplied by this L, we have L square t minus 2. So here now we can conclude that L square t minus 2 equals to what? L square t minus 2 plus 2L square t minus 2. Now having this now for you to add two quantities together, for us to add u square and 2as, that means 2as have the same dimension as u square. And for them to be equal to v square, that means v square also have the same dimension as them. So they are homogeneous. Are we together? This equation is homogeneous because this one have the same dimension as this, and this also have what? The same dimension as this. You cannot subtract or add two quantities of which their dimension are different. You can only subtract a quantity from another, or you add a quantity to another quantity if those quantities have the same dimension. And for them to be equal to another quantity, that means that quantity of which they are equal to must also have the same dimension as them. Now we can see now that this has the same dimension as our 2s, and they are also equal to a particular quantity that have the same dimension as them. These two is a constant, so it doesn't change the dimension for that quantity. Like a constant, a coefficient as a constant doesn't change the dimension of a particular quantity. So the dimension of these 2s is still L squared t minus 2, which is same thing as this L squared t minus 2. And they are both equal to L squared t minus 2. So this particular equation is correct and is valid. So that's one use of dimension analysis to check whether an equation is valid or not. Now, let's move to another aspect. Now, let's say I give you a question like 2y minus 2y. Like you should find the dimension. Say 2y minus 2y. Find the dimension of this particular expression. Are we together? Where y is in meters. Find the dimension of 2y minus 2y where y is in meter. Now, you'll be tempted to say the final stuff you are going to get is 0. Now, mathematically, if you subtract 2y from 2y, you are going to get 0. But as far as dimension is concerned, since our y is still in meter, we can conclude that this guy is 2 meter minus what? 2 meter. Now, for dimension, this is just the easiest way to do it. 2 meter minus 2 meter, you are going to get what? 0 meter. Am I right? Now this meter, this a meter. Now what's the dimension for meter? That's what? That's L. Are we together? Now this 0 here is just like a constant. Every constant has a dimension of 1, meaning that they are dimensionless. When we are saying something is dimensionless, it means the dimension is 1. So for this particular 0 here, it has a dimension of 1. I'm saying 1 for this meter has a dimension of L. So 1 multiplied by L is still L. So the answer is not 0, even though they have the same coefficient. As far as dimension is concerned, the dimension is still L. So that's that for that. Now let's deal with this particular question here. So now the displacement of a particle in an xy plane is given by x equals to at squared plus b and y equals to dt cube minus e, where t is time from rest and a, b, d and e are constant. Find the dimension of a comma b and d. So where t is time from rest and a, b, d and e are constant, find the dimension. We have different types of constants. Initially, I made mention of constant having a dimension of 1. It depends on the type of constant you are talking about. For instance, if we have a constant of just a number like 2, like 3, like 4 as a coefficient of a particular quantity, such constant has a dimension of 1. But you can also have some constant that they have their own dimension. You can have like, let me say, in a particular expression, length can be a constant. In a particular expression, length can be a constant. In a particular expression, let's say acceleration can be a constant. In a particular expression, volume can be a constant, etc. So we are not generalizing that all constants are dimensionless. It depends on the type of constant you are talking about. So is that clear? Now, for this question, now the displacement of a particle in an xy plane is given by x equals to at squared plus b and y equals to dt cube minus e, where t is time from rest and a, b, d and e are constant. Now find the dimension of a, b and d. Now, what you need to know is that first thing, we are asked that this xy plane, one thing you need to know is that your x and your y, their lengths, are talking of xy plane like a number line, like a line on your graph. You know, if you have your graph, this your y and this your x, this is referring to length. Are we together? And your y also is referring to length. Now your x there, and in fact we have been told that this is a displacement rather, so we don't even need that displacement. So your x is a displacement which has a dimension of L. Your y also is a displacement which also have what? a dimension of L. Now, for you to add 80 square with B, for you to add 80 square with B, that means 80 square and B, they have what? The same dimension. And for them to be equal to X, that means they also what? Have the same dimension as what? As X. For you to add dt cube with, for you to subtract E from dt cube, that means E and dt cube, they have the same dimension. And for them to be equal to Y, that means Y also have the same dimension as them. Like anything that doesn't have the same dimension, you cannot add them together. Neither can you subtract them from each other. So being able to add B to 80 square, that means 80 square and B, they have same dimension. And for them to still be equal to X, that means they also have what? The same dimension as X. So if our X is displacement, that means we know that our X has what? Dimension of L, right? And 80 square and B, for them to be equal to X, that means each of them have what? The same dimension as X. So which means that our B also has what? L dimension. Is that clear? Now, that means they also have what? The same dimension as what? 80 square. So now, conclude that 80 square has a dimension of what? L. So we are asked to find the dimension of A. If 80 square also have the same dimension of L, making A the subject of the formula, say your A equals to what? L over what? LT square. That means your A is what? LT raised to power minus 2. So your A has a dimension of LT raised to power minus 2. Is that clear? Now, we found our, since T is in time, we found our A, we found our B to be L. Now, let's get our D and our E. Now, the second expression here is y equals to dt cube minus E. Don't forget, this y is also a displacement, which means it's going to have a dimension of what? Since y is a displacement, the dimension is going to be what? L. And for us to be able to subtract E from dt cube, that means E and dt cube, they have the same dimension. Are we together? They are homogeneous. So, and for them to be equal to y, that means y also have the same dimension as them. Like you cannot subtract acceleration from force. Are we together? And if you are adding two forces together, the answer you are going to get will still give you force. So adding two quantities together is going to give you the same quantity as an answer. And subtracting two quantities from each other is going to give you the same quantity as an answer, even though the magnitude may be different. Like how big, if you subtract 2 from 5, you get 3. So if you subtract 2 meters from 5 meters, you get 3 meters. That 3 meters is still length, it's still a distance. And two things you subtract, they are also distance. So for you to subtract two things from each other, that means they are what? They have the same dimension. And for them to be equal to another quantity, that means that quantity also have what? The same dimension as them. And since our y is displacement, that means E also what? We carry the dimension for y. So if our y has a dimension of L, our E also will also have what? Dimension of L. Are we together? Now, let's look for D. You know, dt cube also must have the same dimension as E. So that means our dt cube now, we have a dimension of L as well. So finding the dimension for D, we can conclude that our D equals to what? L over what? Because since our T is in time, the dimension for time is what? T cube. So at the end of the day, our D is what? LT raised to power what? Minus 3. Is that clear? So now we can conclude that we have to find the dimension for A, B, D, and what? And E. So our A is what? LT raised to power minus 2. Our B is what? L. Our D is what? LT raised to power minus 3. And our E is also what? L. These are the four answers. So these are the basic understanding you need on dimension. Now before we end the class, let's quickly see another question. So now let's say if you have A cube minus Z equals to P, where P is in meter and T is in seconds. Find the dimension of A and Z. So this is a particular question. 80 cubed minus z equals to p, where p is in meter and t is in seconds. We have to find the dimension of a and z. Now, since our p is in meter, that means p has a dimension of what? L. And subtracting this z from 80 cube, that means z and 80 cube, they also have what? The same dimension. And for them to be equal to p, that means this 80 cube and z, they also have what? The same dimension as what? As p. And since our p has a dimension of L, that means z also has what? Dimension of L. And since we are able to subtract in the equation, we are subtracting this z from 80 cube. And that means 80 cube and z themselves, they also have what? Equal dimension. So if z equals to L, that means 80 cube as well will be what? L. Now finding the dimension of A, since our t is time, is in seconds, that means A give us what? L over what? T cube, and that's what? LT raised power what? Minus 3. Just get the basic idea. For you to be able to add two quantities together, that means the two quantities have the same dimension. For you to subtract a quantity from each other, that means they have the same dimension. And for them to be equal to a particular quantity, that means they also have the same dimension. So that's that for that. Now, before we call it off, one thing you also need to know is some quantity have units, but they don't have dimension. For instance, like radian, if I say the angle between two forces is 80 degree, that 80 degree, the unit is in degree. It has a unit of degree. The unit at which we measure an angle is in degree, but there is no dimension. It doesn't have dimension. It has units, but it doesn't have dimension. The dimension is just, it has a dimension of 1. Dimension equals to 1. When we say quantity does not have dimension, that means the dimension is 1. So we have some that have units, but they don't have dimension. So not all dimensionless quantity are unitless. Some quantity, they don't have dimension, but they have units. But there is no how a quantity can have dimension when the quantity do not have units. But a quantity can still have units without a dimension. But you cannot have dimension when you don't have units. For instance, let me write this out. If you say all quantity and all unitless all unitless quantities are dimensionless, if I say all unitless quantity are dimensionless, this is certainly true. That's very correct. Because if you don't have units, you cannot have dimension. Without units, a unit is just like an identification. If I cannot identify a quantity with its unit, there is no way such quantity can possess a dimension. So without units, there is no dimension. But if I should say all all dimensionless, if I should say all dimensionless quantity are unitless, this is not true. Why? Because we have some that have units, but they don't have dimension. Like the first one I did, 80 degree. The unit is in degree, but what? It doesn't have a dimension. For this first one, is very correct. Without units, there is no dimension. But we have some without dimension that they still have units. So that's that for that. Thank you for watching the video. So see